So in section 2, we're going to talk about some common graphs used to represent quantitative variables. And we're going to start with the histogram. So at the end of section 1, we talked about bar graphs and how those bars could not touch because there was a different graph where the bars did touch. And that's what a histogram is. It is a bar graph where the bars touch. And the way you organize the data is through something called a bin, where you determine a range of values and you figure out how many numbers in your data set fit into that bin. So a histogram is a display of a range of values. So the downside to a histogram is that you lose the data when you graph it. So you're no longer able to see the numbers. You only know how many numbers fall within a range. You don't know where in that range they fall. So I've already predetermined the size of my bins for our example with combined scores for 2 weeks of NFL games. And I'm going to do bin sizes of 10. So the first number of the bin is what is going to go along my x-axis when I graph it. So if I want to go up by 10s, 15, 25, 35, 45, etc., my previous bin can't include the first number of my second bin. So if I want to go from 15 and I want to go 10, I have to include in that range any of my numbers that fall between 15 and 24. So if you, as you're going through your data, it's a good idea to mark a number once you've counted it so you make sure you have included all of your numbers. So I've gone through and done this already. So there are 4 numbers that fall between 15 and 24. 3 that fall between 25 and 34, 13 between 35 and 44, 6 between 45 and 54, 3 between 56 and 64, 2 between 65 and 74, and then 1 between 75 and 84. Now we can go about making our histogram. So just like any graph, it does need a title. So I'm going to make my title NFL scores. Similar to a bar graph, the y-axis is going to be the count. And then in this case, my x-axis is going to be my scores. So my largest number in a bin is 13. So I need to make sure my y-axis goes up to at least 13. And I'm going to go up by 2s. I'm going to go up to 14. And then for my histogram, I don't have to start at 0 in my histogram. I can start at my first bin. So my first bin is at 15, and then my next one starts at 25, 35, 45, and even though I'm not going to have a bin at 85, I do need to have an ending number for my last bin. Another thing to keep in mind is if you end up with a bin with no numbers, like if I didn't have any scores between 65 and 74, I cannot skip it on my graph. What ends up happening is I'll just have a space there drawing my bars where they don't end up touching. So now I'm going to start. So I'm going to go up to 4 between 15 and 25. And then my next bin is just going to build off the previous one. So then 3. Then up to my 13. Then 6. Then 3, 2, and 1. And that gives us our histogram. One other thing I want to briefly mention is that when you're trying to determine your bin width, you want to make sure you're looking at the range of your data. So you don't want to have your bins be too wide, and you also don't want to have them be too small. And this is going to come into play when we talk about section 3 and we talk about shapes of distributions. So the larger the range of your value set, the larger the bin width you're going to have. And then the smaller the range is, so the closer together the data is, the smaller the bin width will be. On this page of your notes is just example on the steps, I should say, on how to enter the data into the list of your calculator, and if you have a TI-84 or even an 83, and how to do a histogram on your graphing calculator. So if you have a chance, read it over, make sure you can do it with that previous example, and if you have any questions, just let me know. So the next type of graph we're going to discuss is a stem and leaf plot, or a stem plot. So what we did in class as an activity is for 20 seconds, you took your pulse rate and then you tripled it, and you did that 3 times, and then you took your pulse rates that were tripled and found the average. And then we have a class data set here of average pulse rates. And what we're going to now do is organize this data in a stem plot. So it's not a graph in the traditional sense, because it's just a way to organize numbers, but it's better in one way to a histogram because you don't lose your data with a stem plot. I'll be able to see all the numbers still. I'll know exactly what they are. I haven't lost them in my bins that are just arranged. That's really the only upside to a stem plot. You can still see shapes of distributions for stem plots, but there's really not much other benefit to a stem plot. So the way a stem plot works is your stem typically represents your tens place, and then your leaf represents your ones place when we're talking about 2-digit numbers. If you have a 3-digit number, your stem then represents the hundreds and the tens place, and then your leaf is still the ones place. And then another difference is, instead of having a title or axis labels for a stem and leaf plot, we always have a key for the graph, so someone can come in, just look at the stem plot and know what your data represents. So when we're creating our stems, you look for the lowest heart rate, and that tells you what your first stem has to be. So my lowest heart rate is 50. And then your largest number, which is 99. So I have to include every stem from 5 to 9. If it happens that there isn't a number in one of those stems, you cannot skip it. So if there weren't anyone whose heart rate is in the 80s, I can't skip that and do 5, 6, 7, 9. I have to include it. There would just be no numbers written there. So similar to a histogram, where if there ends up being no numbers in a bin and you can't skip it, same thing with a stem plot. And now if you have multiple numbers that fall in a stem, they do have to be in numerical order. And again, you want to keep track of your numbers as you write them down so as to not forget any. So we have just one number in the 50s, and that is 50. Then in the 60s, there are 2. So we have 63 and 64. And you also want to make sure when it comes to the spacing, as you're going down, the leaves line up so that the spacing is even across. Okay, so in the 70s, there are 2 70s and 2 71s. Then 72 and 72 73s. 74, 75, 2 76s, and a 77. And then in the 80s, there is an 83, an 85, and an 89, and then our 99. And you can always double check that you've included all your numbers by counting the numbers that appear in your leaf and making sure it matches your data. So there should be 19 there, and there is. So now when it comes to our key, you can pick any number from your stem and leaf plot, doesn't matter which one you choose, for your key. So I'm going to do 7, and then I'm going to do my bar in 3, and then that is going to equal 73, and then you do want to make sure you include your units for your problem. So 7-3 equals 73 BPM, or beats per minute. So it gives an idea of what your data is representing. The next graph is a second type of the stem and leaf plot, which is a split stem and leaf. And it is used when you have too many data values in a single stem. So if your data falls closer together in a range, typically you're going to end up using a split stem and leaf, because otherwise your stems end up being too long. So it kind of goes to, if your bins for a histogram are too wide of a range and you don't have as many bins, it's misleading to the shape of the distribution. That's kind of why we use a split stem and leaf, because if I did a regular stem plot, I wouldn't have as many stems, which would lead to a misrepresentation of what the data actually looks like. So you set it up the normal way. So you're going to have your stem and your leaf. Okay. Then you're going to start with, all right, what's my smallest number? In this case, that's 62. So when you split up your stems, all right, you always have 2 of each. The first leaf for that stem is always the digits 0 through 4, and the second one is always 5 through 9. So you split it in half. And then our highest number is in the 90s, so I have to have 7, 7, 8, 8, and then we'll do our 9, 9. And then the rest of this is just like a previous stem plot. So there is a 62. And I'm going to cross these numbers off as I use them, which is the only number in the 60, in the lower end of the 60s. And then there is a 69. Okay. In the 70s, there is a 74. And then a 75. 78 and 79. The bulk of our data is going to fall in that 8 of our stem leaf. So the 80 to 84 and the 85 to the 89. So there are 2 80s. And an 82. And an 84, two 84s. And there are 1, 2, 3, 4, 5 88s. And then we have 2 90s. Three 92s. A 93 and a 94. And then a 96. And then we're going to end it with our key. So I'm going to do 7-8 equals 78. Now, typically speaking here, all right, I'm going to go ahead and put percent. You're not able to assume when you have scores for a test like this one that it's necessarily always a percentage. In this case, between my numbers are between 60 and like the mid 90s, you can go ahead and assume it is a percentage. If my numbers were smaller, like between 12 and 20, then the total number of points is probably smaller. So we would say that it's points. You can also put points here if you're unsure. It will also work, because even if it is 78 out of 100 as the total, 78 points corresponds to 78%. One of the easiest graphs we're going to talk about graphing is a dot plot. So it's a very simple graph that involves plotting data values with dots above the corresponding values on a number line. So to construct your dot plot, you just need an x-axis and then a title. So you draw your horizontal line, label it with the variable, scale the axis based on the values, and then mark a dot above that number corresponding to each data value. So we have a quiz score out of 50 on a past exam, so we're going to construct our dot plot. So my title is going to be quiz scores, and then I can go ahead and put out of 50. Okay. So when I do my x-axis, I do not have to start at 0. I can start at whatever the smallest number is, and then my max can just be my biggest number. And I don't have to go up by ones. I can go up by a different scale. And then my x-axis is just going to be labeled scores. So I'm looking through here. The smallest number is 26. So I'm going to start with 26, and then I'm going to go up by 2s. I need to extend my number line a little bit. And I am going to go up to 50 because there are a couple scores that are 50. And the nice thing is here, you don't have to organize the data in any way. You can literally go in the order it appears and just place your dots. So my first dot is going to be over 36. Then I have 1, 2, 3, 4 42s. And again, you do want to space your dots consistently as you're doing this. Then 26, 38, 32, 30, 42, 34, 44, another 44, 34, 48, 2 more 42s, 34 and 38, 50, 3 38s, and a 44. And there is our dot plot. Like I said, it's the easiest graph to do of quantitative variables. It's just a number line and then placing dots, and you don't have to worry about organizing it in order like you do with a histogram or a stem and leaf plot. So the last type of graph we're going to talk about is a cumulative relative frequency graph. And we're going to talk about it because it is a way to display quantitative variables, but we're not going to use it very often. It's not really a great graph to actually look at data. It doesn't help with shapes of distributions all that much. So we don't typically use them. They're also known as ogives. They are used to display percentiles, and there is a much better graph that we're going to talk about to display percentiles. So just to review, a percentile tells you the percent of data that falls below that number. So you have to first make a table of the cumulative relative frequencies in order to graph it. And it can be done one of two ways. So I'm going to show you both ways, and they both result in the same graph. So it doesn't matter which one you choose to do. I find one way to be a little bit easier than the other. So you can find the relative frequencies first, then find the cumulative percentages, or you can do cumulative frequencies and convert those percentages. I find the second method to be a bit simpler. So the example we're going to do looking at as ages of the U.S. presidents when they took office. And then this is current with Donald Trump through his second term. So I only counted his age for his first term on here, but it does have the total number of presidents. So I started at 40, so 40 to 44, 45 to 49. So similar to a histogram, your data does have to be grouped by ranges. So you don't look at single individual values, you do look at the values in a range. So I have it going by fives, starting at 40 up to what is basically 80. So we have 2, 7, 13, 12, 7, 3, 1, and 1. So the first thing I'm going to do here is find the total. So we've had 46 presidents. This does not include presidents who served multiple terms. So it's just saying someone who has served as a president, no matter how many terms they've served, we've had 46 of them. So the first way where you do relative frequencies is you're going to take the frequency, so the number that falls within that range, and convert it to a percentage. So we have 2 over 46, 7 over 46, 13 over 46. So all of these are going to be written as fractions. Now I'm going to go ahead and convert all of these fractions to percentages. And I'm going to do whole number percentages just because when we get to the graphing part, it's easier to go based off whole numbers. So 2 out of 46 is roughly 4%. 7 out of 46 is 15%. 13 out of 46 is 28. 12 out of 46 is 26. Another 7, so 15% again. 3 out of 46 is 7%. And then 1 out of 46 is 2%. So now when I do the cumulative relative frequency, the first percentage always stays the same. So the total number of presidents so far that have fallen in your age range is the first one, is just 4%. So now you're adding as you go. So now at 45 to 90, you're finding the total percent of presidents who have basically are between 40 and 49. So you're going to do 4 plus 15, which is going to be 19%. And then we take that 19% and we add our next percentage, which is 28. Which is 47%. Then we do 47 plus 26, which is 73%. Then 73 plus 15, which is 88%. And then 88 plus 7, which is 95%. 95 plus 2, which is 97%. And then 97 plus 2, which is 99%. So this is why I don't like this method as much, because you're not necessarily always going to end up with 100% at the end, because I converted it to a percentage first, and that percentage was not exact, and I had to do rounding. And because of some rounding errors, I don't get something that is exactly 100%. So we're going to say it's roughly 100% at the end here, because I have reached the end. That is all of my numbers. It should be 100% at the end. All right, so now let's talk about how you create the graph from these percentages. So you're going to have an X and a Y axis. So we've got president, ages at inauguration. So my y-axis is going to be my relative cumulative frequency. So the relative cumulative frequency as a percent. And my y-axis is going to be labeled as my age. So then, similar to a histogram, you're going to start with the first number of your range. So 40, and we went up by 5s. And then we're going to go all the way up to 80. And then for my percentages, I'm going to make it easy, go up by tenths. So the way it starts, so my cumulative percent, so like this would be 0, you technically start at 0. My cumulative percent at 40 is 4%. So I'm going to put a dot at 4%. Then at 45, it's 19. 50 is 47. 55 is 73. Then 88, 95, 97, and 99. And then you connect it with lines. So it's not a curve, it's lines. Now, it will approach a curved shape as you do this. So it does approach the shape of a curve, but you do draw it by connecting lines. And this is what we call an ogive. So it's not great at helping us with the shape of a distribution because they're all going to start low and then increase as the numbers go up because your total percent is approaching 100. So that's why we typically don't use these graphs so much, is because they're not helpful in shapes of distributions. It's just a big part of graphing data is trying to figure out what that distribution looks like. So the second method, which is the method if you're going to create it, is to find the cumulative frequencies and then convert to a percentage. And I much prefer this one. So my cumulative frequency is adding the numbers that fall within the ranges as you go and then just doing percentages right away. So the first one stays at 2. And then you do 2 plus 7, so you get 9. Then 9 plus 13, which is 22. 22 plus 12, which is 34. 34 plus 7, which is 41. 41 plus 3, which is 44. 44 plus 1, which is 45. And then 45 plus 1, which is 46. So this way you're guaranteed to get 100% at the end because now I'm going to treat them as fractions. So I'm going to do 2 over 46. So the first percentage doesn't ever change. So that's still 4%. And now I'm going to do 9 over 46. Which is 20%. 22 over 46, which is 48%. 34 over 46 is 74%. 41 over 46, which is 89%. 44 over 46, which is 96%. 45 over 46 is 98%. And then obviously 46 over 46 is 100%. So the percentages are pretty close to what we had before, but this time they're just slightly more accurate. So no matter which method you choose, you're not going to get percentages that are super far off from one another, but the second method I just find to be slightly more accurate. So the graph, you're going to construct it the exact same way. So you're going to have your x-axis and your y-axis, age, and then cumulative relative frequency as a percent, title, president, ages at inauguration. Still going to do my percentages by tens. And my age, 40, 45, 50. All the way up to 75. And now I graph my frequencies. So obviously you start at 0. We're going to do 4% again. Now we're going to do 20, 48, 74, 89, 96, 98, and 100. And then you connect them with the lines again. Slightly off with that dot. And as you can see, it's pretty much the same percentages, just because of rounding, they're slightly off. And then we have basically the same graph. You can make it look like a histogram. So if you wanted to, you can now, like, as you're going up to the percentages, you basically just make them, so like from the 40 to 45, and then it goes up and over. So the dot is the beginning of the next bar, not the, oh, very bad at my lines towards the end. Not the end of the previous one. But it's not a great way to look at it through the histogram lens, because again, it doesn't really give us a good idea of the shape of the distribution when we talk about it in section 3. So I don't really like to convert it to a histogram. And like I said, we're not really going to graph using this because there's not really a huge benefit to it. There's a much better graph to use when looking at percentiles, and we'll talk about that later. So let me know if you have any questions about any of the other types of graphs used to display quantitative variables.